Good morning, students. Today I am explaining dual linear programming problem. So what is the definition, introduction of duality linear programming problem? So every LPP is associated with another LPP. Every LPP is associated with another LPP. The original problem is called primal LPP, and the other problem is called it's a dual LPP. The relationship between the primal and dual is very useful. That's why it is known as dual linear programming problem. If the given problem is known as, that is called original problem. That original problem is called primal LPP, and it's a dupe means, and it's another form. Another LPP is called dual LPP. So the relationship between the primal and dual is very useful. The optimum solution of one form, either primal. If you know the primal optimum solution, we can find dual solution. Suppose if you know the dual optimum solution, then we can find primal solution. That is a benefit of the duality. So the optimum solution of one form of LPP reveals the optimum solution of the other. So this is the introduction about dual linear programming problem. So there is a little bit change compared to our LPP. So that's why see the procedure of changing primal LPP into dual LPP. If the given problem means original is considered as primal LPP, then the following procedure can be utilized to change a primal LPP into dual LPP. Means if the original problem, you have to convert into dual problem. So there is a procedure for that, just 4 steps for that. So first one is, if the objective function is, suppose if our objective function is maximization, then convert it into a minimization. Suppose if it is minimization, convert it as maximization. So that is vice versa. And then the cost vector of the objective function in the dual LPP is considered from the right hand side vector of the constraints in the primal LPP. So if in our objective function subject to the constraint, suppose these are the suppose maximization problem. If it is maximization problem, convert it as minimization in the case of dual LPP. And then come to the constraints. What are the constraints here? See the second step, the cost vector of the objective function. The how you are getting the objective function in the dual LPP. Objective function means this is the objective function. How you are getting 835 values? So wherever the cost quotient, all the BIs, nothing but wherever the constraints of the BIs are considered as a cost coefficients of the objective function in the dual LPP. I will give the brief explanation with example. And the third step is the constraint coefficient matrix of dual LPP is obtained by the transpose constraint coefficient matrix of primal LPP. If all the constraints in the primal LPP are less than, then change in dual as greater than or equal, and vice versa. If it is greater than, then convert it as less than in the dual LPP. For this, we have the various primal dual pairs. So in formulating dual LPP, there are different kinds of primal dual pairs which are discussed below in the matrix form. So various primal dual pairs. So if it is primal, what is the primal? Max Zx, but still now we know that Z equals to Cx. But in the case of duality, max Zx equals to Cx, and subject to the constraints are Ax equals to B, and constraint and the non-negative variables. So what are the variables available in the constraint? Those variables should be non-negative, means that is positive. So this is the dual, this is the primal. So this you have to convert it as, this is the original problem, you have to convert it as dual problem. So here they given maximization, so convert it as minimization. So zx, in the place of variable x we are taking zw, so equals to cx b transpose w. Say I am telling x, in the place of x you have to consider w, but in the place of c. So already I said that according to the procedure, so this B transpose means all BAs of the constraints, all BAs of the subject to the constraints, that you have to consider as the cost coefficients in our objective function, and subject to Ax equals to B, in the place of x as it is W. So A transpose, which is greater than or equals to, what are the cost coefficients in the objective function, that you have to consider as the BIs in the dual LPP, and the what is the variable here? W. So W is greater than or equals to 0. This is also known as systematic form. And another form is max zx equals to cx subject to the constraints ax equals to b and x greater than. What is the difference in the first case and the second case? In the first case, here you have to take ax is less than or equals to b. In the first case, ax is less than, that's why in the dual LPP, subject to the constraints are greater than. Here it is less than, you have to get greater than. In another case, here in the second case, ax equals to b, here but you are taking as greater. If ulta palta means less than means greater than, then only it is known as symmetric. In the case of unsymmetric form, if it is equal, then we can consider it as greater. That's why here w is unrestricted in sign. So remaining things are as it is. Zx equals to cx, ax equals to b, x greater than or equals to 0, minimum, maximum means minimum, ax equals to b, but it is unsymmetric. That's why you are taking equals to means you are taking here greater than and the remaining as it is. And one more case. So max zx equals to cx. There is no change in the primal, only changes in dual. So max minimization subject to x equals to be a transpose w. So here equal, one time greater than, another time less than. So these two are the example for unsymmetric form. And then fourth one, primal minimization. Till now, in the first three cases in the primal we are taking maximization. And then the fourth one, minimum zx. Suppose if it is our objective function is minimized, then you have to know that case also. That's why if our in the original problem, if we are having minimum zx and the remaining subject to the constraint x equals to b and x greater than or equals to, already you know that according to the procedure, if it is minimization, here we are take maximization zw b transpose w, here equals to, so less than, so unrestricted. So if it is minimization of zx in the case 5, primal minimum, there is no changes in the minimum cases. Then come to the dual. So if it is minimization, convert as maximization zw b transpose w, but here you are taking x greater than or equals to b. That's why here you are getting less than or equals to, little bit changes only in the subject to the constraint, no changes in the objective function as it is. So how you are getting this question? Define dual linear programming problem and obtain its various primal dual pairs. Means you have to write down the definition and these 5 various forms of the dual, primal and dual. And I am giving one example for conversion of if it is LPP, if it is primal LPP, convert it as dual LP. A simple thing. This will be helpful for doing the duality problems, also. That's why these are not important for the exam purpose, but you have to know that. Obtain the dual LPP to the following LPP. Max z equals to 2x1 plus and subject to the constraints less than and x1 x2 are greater. This is the original problem. Then it is known as primal problem. So but this original problem you have to convert it as dual problem. So by observing here in the primal, there are how many variables? X1, x2. How many variables? 2 variables. How many constraints? 1, 2, 3. So that's why you're writing 3 constraints. This is about the primal. This is about the original means. So then how to get the dual? In dual consists here based on 3 constraints we may get 3 variables. Based on variables we may get coefficients. So just vice versa. So 3 constraint means 3 variables. 2 variables means 2 coefficients. The given LPP can be written in the matrix form as follows. First, we are writing the given problem as a present as primal. So in primal, C equals to, what is the C? This is the Z equals to Cx. C means constant 2, 5. X, what are the variables? X1, X2. And capital A equals to, what are the cost coefficients of the constraints? 3, 4, 5, 6, minus 2, 4, and B values are BS 8, 3, 5. Now the matrix form, just we are representing in the matrix form. So that implies max zx equals, just we are writing the LPP means max objective function subject to the constraints and non-negative restrictions. According to that, just we are substituting max z equals to Cx. Already we know that C is say Cx and Ax less than or equals to B, and this is about the primal. Based on this information, we have to convert it as dual. Then the dual of the above problem then the dual of the above primal in the matrix form. Already you know that here they given um, x less than. If you see the constraints, all the constraints are less than or equal to type. That's why you are writing. Already we discussed the various pairs. In that we can, based on the given problem, we can write this primal. According to that we can represent the dual also. So in the problem they given maximization, that's why here you are writing minimization, and in the problem they given less than or equals to the b, that is the constraint. So obviously here you have to take greater than or equals to c power t. So then what is the W here? What are the constraint? What are the variables W1, W2, W3? Now the dual LPP is minimum ZW equals to B transpose W. What is the B here? 8. B is 8, 3, 5. B transpose means this is the row column matrix, so it is converted as row matrix. So B transpose W means W1, W2, W. So this is the objective function. And subject to the constraints A transpose. What is the A here? 3, 4. This is the two 3 rows 2 columns, so it is a transpose becomes two rows. So this is the 3 rows 2 columns, here 2 rows 3 columns transpose means. So w1 w means just represent the variables, and c transpose means what is the c? 2, 5 is a row matrix, but here it is a column matrix. So then 3w1 plus 5w2 minus 2w3, which is greater than or equals to 2, and 4w1 6w2 plus 4w3, which is greater than or equals to 5. Therefore minimum z equals to, from this matrix, minimum z equals to 8w1 plus 3w2 plus 5w3. So on non-negativity restrictions of w1 w2 as what are the variables are available, that are always non-negative. Therefore dual of the given LPP is minimum zw equals to 8w1 3w2 plus 5w3. So this is the objective function. These are the subject to the constraints and non-negativity restrictions. So this is the maximization problem. This is the minimization problem. So here we are getting the given minimum. So you have to get in the dual maximization. So what are the how many variables are available here? 1, 2, 3. How many constraints? Constraints also 3. So here also you may get 3 constraints and 3 variables. So in the dual there are 3 variables and 3 constraints. The given LPP, whatever that they given, you have to represent. See this C values, X values, AB values, and then matrix form of the LPP, matrix form of the primal LPP. Based on that we can convert it as dual. Just simply the given maximization, so convert it as minimization. How you are getting 6? These are the BIs, but in the place of X you have to write W's, and then A transpose along with W1. Here the given the constraints are all are less than or equals to type. So you have to get greater than or equals to type. So this is the final solution.